Hi there. In this video, we're going to be talking about line integrals. The next few videos are going to focus entirely on integration in terms of multivariable calculus. Line integrals do form part of that, and they're also going to come in when we look at vector calculus. However, this serves as an introduction to what it actually is. And what it actually is simply a function that's being integrated along a curve. Perhaps the easiest way to conceptualize line integrals would be to think about work done. If we have an object that's on the floor and we push it, in other words, we apply some force, perhaps that force is Ft, and then it moves a certain distance, delta S, then we would know from physics that the work done, W, is Ft delta S. So the work done is, of course, the energy required to move this object, this block, this distance delta S. So a line integral sort of follows that same thinking and that same methodology. It's a function that's acting across a certain distance. However, we would think about it in terms of a curve rather than a distance. So we can take that same example and we would look at it specifically in terms of a curve. Perhaps we could think of a roller coaster. And a roller coaster, of course, has a certain path that it follows, a trajectory. And it would start at the top of this incline, and then it would, of course, move downward. If we just take a snapshot when it's at the center, and if we just look at what's happening, what are the forces acting on the roller coaster? Well, it's the force of gravity. Call it Fg. So this gravity has two components. The one component is the tangent force. So we would think about the tangent as acting in that direction, and we would also think of a normal force, and that normal force is acting perpendicular to the surface of the track that the roller coaster is on. We'll call that Fn, and Ft is the tangential force. So we want to calculate the work done. How would we do that? What is the work done? We saw just now that the work done is just the force multiplied by the distance, right? So if we just think of a small distance, so that small distance is the length of this curve or this arc length, and we can call that delta S. So the work done is just going to be the force in the direction of delta S multiplied by delta S. So the work done would be Ft times delta S. So if we wanted to calculate the work done traveling from the top of this roller coaster to the bottom, maybe from point A to point B, then what we would have to do is we would have to add up all the chunks of delta S from A to B. So perhaps the work done, or let's call it I, the line integral. So the line integral from A to B, well, not the line integral at this stage, we're just calling it work done. But anyway, it's the sum of all these little chunks of delta S added up from A to B. So it's the sum of this tangent force. And of course, each point will have its own tangent. So there'd be a tangent there at that point, maybe another tangent like that. And we would have to add up the delta S's associated with each one of those tangents. So of course, we would also remember from single variable calculus that if we let delta S become infinitely small, then delta S becomes ds, an infinitesimal quantity. And then if we sum up the infinitesimal quantity between 2 points, then that summation becomes an integral. So we're integrating along the curve AB of this function ft, which we're thinking of as the work done in this context, multiplied by ds. So this is the line integral. So this, when we speak about a line integral, we're talking about this integral of some function along a certain curve or along a certain distance between 2 points a, b. So this is our definition of an integral. So we need to take this just a little bit further. Sometimes it's not very practical to be integrating something along ds. And of course, there are ways to get around this, and perhaps we would look at something like that in later videos. But if we were to just break apart this red component, force component, and we just write it like that, and we can see that the work done is ft, that's a t, delta s. So what we're going to do is break this up into two parts. So instead of this quantity, ft delta s, we can think of two other quantities that we are now defining. We'll call it q delta y and p delta x. So we are creating these two quantities, p and q, such that ft delta s is equal to the sum of these two quantities. So we have chosen p and q specifically so that it's equal to this ft delta s. So ft delta s is equal to p delta x plus q delta y. And of course, if we make delta x and delta y infinitely small, as we have done with delta s, then we can just substitute this into our line integral. So that would mean that I now becomes the integral of, or rather between AB of p dx plus q dy. So you might be thinking to yourself at this stage, okay, I've seen this thing before, p dx and q dy. In fact, I've seen it quite a lot if you've been looking at the previous videos. And you can see that we expressed function differentials in the form dz is equal to p dx plus q dy. So does this have anything to do with line integrals? The answer to that is yes, it does, but we're not going to go there just yet. There are a few other things we want to speak about and consider before we actually consider line integrals and differentials and exact differentials and what they all mean. So before we proceed any further, I think the next best thing would be to look at a simple example of how we actually calculate a line integral. So we have a certain curve, and that curve is y is equal to x, or rather 4x to the power 2, 4x squared. And this is defined with x and y greater than 0. And we have 2 points, O and B. And the curve between these 2 points is 4x squared. So it looks something like this. It's a quadratic. And where b is equal to 1, then y is equal to 4. So we want to do a line integral between O to B of a certain function. And that function is the integral of x squared plus 2y dx plus xy dy. So this is, of course, our p, and this is our q. We don't really need to do anything with it being q and p and q at this stage. We just need to evaluate this integral. So between these 2 points, the curve is y is equal to 4x. So that means that dy is equal to 8x dx. So we simply substitute dy inside our line integral and 4x squared where we have y. So then doing that, and of course our integration bound is x, since we are making x the subject of our integration. So we're integrating from 0 to 1. So that's x squared plus 2y, so y is 4x squared, so 2 times 4 is 8. So we have 8x squared dx plus, well, we have x is just x, and then we are multiplying this by y, which is 4x squared, and we have dy, and dy is 8x dx. So proceeding with this as we would generally do, we just simplify it a bit. So x times x squared times x, this is going to be x to the power 4, and 8 times 4 is 32. So we would have x squared plus 8x squared, that just gives us 9x squared. And we saw that this is 32 x to the power 4 dx. Then integrating this, x squared becomes x cubed. 3 times something must give us 9. And of course, 3 times 3 is 9. X to the power 4, so this becomes x to the power 5. Then 5 times something must give us 32, and that would give us 32 over 5. 5 times 32 over 5 gives us 32. And we're integrating from 0 to 1. So, of course, 0, nothing is going to happen here. So we substitute in 1, and then what we're left with is 3 plus 32 over 5. And this is just 47 over 5. So this is how we determine a line integral. It's just some function that we are integrating along a curve between 2 points. And the easiest way to think about a line integral, an example of that would be the work done. So in the upcoming videos, we're going to be looking at how we integrate around a closed curve, and then how we apply line integrals to closed curves, and then the relationship between exact differentials and line integrals.